All right, so as you know, we already did all this last year, right? We studied all of kinematics last year, so we are absolutely not going to spend an entire, month going over kinematics like we did last year. So we have to know what we know from last year. We have to remember that stuff, which is why you're getting the summer packet, right? The summer packet was a way for you to recall that information and have it kind of ready firsthand when you need to use it. So kinematics-wise, give me a formula. Don't look at your formula sheet. You should have some of these memorized by now. Give me a kinematic formula, just one. I just want one from each person. Vita, give me one start.
V equals V initial plus A times T.
Nice. That's one of ours. Josh?
X equals X half plus mu naught T plus 2AT squared.
Nice, Josh. Gustav, the last one?
It was V squared is equal to V naught squared plus 2A delta X.
Nice. So those are the three main kinematic formulas we looked at. And all three of these formulas involve what variables? What variables is in all three of the formulas? And I say variables, obviously, so you can give multiple answers. Connor?
Velocity, acceleration, and displacement.
Close. Velocity and acceleration. Displacement is not in the first one, but yes. Acceleration is in all three. And then initial velocity specifically is in all three. Okay? The final velocity is not in all three, right? It's not in the middle one, so there's no final velocity here, and there's no displacement here, and there's no time here. So it's really useful to write down what's missing in each of these, right? So there's no, in this case, we said delta x. In here, there's no final velocity, and here there's no time. And I write those down because the minute I'm given a problem that doesn't involve time, there's really only one option, right? It's the third formula. If I'm given a problem that doesn't involve displacement, I know that I'm not going to use the second and third. I got to use the first formula. So when I recognize what I'm given, I can easily choose my equation properly. Again, I'm not going to review problems on basic kinematics. What we're going to do next now is apply calculus to it. Step me through where you're at in calc right now. You've learned about the derivative?
We learned about the derivative.
Good. Have you learned the power rule?
Yes.
Okay.
This weekend's homework, actually.
Nice. Great. It always works out timing-wise, and I try to wait a little bit for this. That's why we do linearization to start the year, because it gives you time to go through derivatives. So you did the definition of the derivative, like the difference quotient, all that, limits? Good. All right, so I'm not going to review all that stuff, because you should know that. Physics will not ask you for the limit process to get the derivative. Calculus will. So you have to know that. You could be asked a question on that. But for physics, you need to know your power rule really well. Power rule comes up all the time. You're going to learn later about what's called the quotient and the product rule, and then there are some trig rules. The trig rules could play a role here also, but mainly the power rule, and it's really easy, obviously. The power rule is not hard.
Multiply and then subtract.
Yeah, you bring down the exponent, multiply it, and then reduce it by 1. It's really easy. And later on, you're going to learn about something called integration, which I'm going to...
reverse it out.
Yeah.
Multiply and then increase by 1 or something.
You increase it by 1 and you divide by the new exponent instead of multiplying by it. Yeah. Yeah, instead of multiplying by the old exponent, you raise up the power to a new one and you divide by it. And it's called the antiderivative. The integral is the opposite of a derivative. So what we want to talk about now, so you have these three formulas, right? They're in your head? Okay. Now if I take a look at this problem, can somebody make a connection between two of the formulas involving derivatives?
Yes.
Is there a connection between two of these formulas involving derivatives? Conrad, go ahead.
Isn't the first one the derivative of the second one?
Nice, well done. So this is your position function, really. And we learned that last year. We called it the position function because it measured the position of an object at some point. This is your velocity function. Now, in calc, you may not have learned this yet. The derivative of position is velocity. The derivative of velocity is acceleration. They're connected to each other. So when you, as Conrad noticed, when you take the derivative of equation 2 here, you get equation 1, because you're taking a derivative of a position function and you're yielding a velocity function as a result. Okay, that will always happen. Derivatives of each become the next. Integrals are the opposite. So let's take a look at some examples of how this can be applied. Can I go to the next? You good? Okay, so you're writing stuff. All right, so let's say that our position function, and this happens a lot, is given as x of t equals 2t squared plus 3t minus 4t cubed plus 8. A problem will say something like this. Given the position function as the following, determine when the object comes to rest. At first, this seems very difficult because rest. Because this is a position function. How is a position function going to tell you when something stops? It's only giving me the position of the object, right? It doesn't tell me when it actually stops. What do you think?
We find the derivative so that we have an equation for velocity.
You find the derivative. Let's do that. So x prime of t, is this how you write derivative yet? Okay. Is equal to v of t, which is equal to, Josh, give me the derivative for this one.
4z plus 3 minus 12t squared.
Nice. And nothing at the end, right? The 8 becomes nothing. Derivative constant is always 0, right? So that's our velocity function now. So as a result, if we gain the velocity function from using a derivative, what can we now do? I want to know when it comes to rest. What does rest mean to you? What does rest mean? What do you think? Conrad?
When it's equal to 0.
Nice. When the velocity function is equal to 0. So it's very common in an AP problem, and this is so easy, by the way, to do this. You just take a derivative and you set it equal to 0. It's a common multiple choice question, and it's like a freebie. It's a gift. And you'll see at least 3 or 4 of these where they involve basic derivatives and basic integrals with motion. Okay? How would you solve this, just so we know? All right, quadratic formula. I assume it may not work, by the way. I made up the numbers. So if time comes out to be imaginary, just bear with me here, okay? But time should be a real quantity. Hey, by the way, at this point in time, you should definitely have the quadratic formula written in your calculator. You should not be graphing it. You should not write out the quadratic formula here ever. You should have a quadratic program in your calculator. If you don't, remind me, and I'll send you a video how to program it yourself. You just put in A, B, and C, and you get an answer. It's just time. You don't want to waste time on an AP physics exam. No one finished this test. Not no one, but very few kids finish the test.
Really?
So, yeah, which is great. It's a lengthy test. It's all right. It's meant, listen, if you get like 60% on the test, it's a 5. It's made to be skewed that way, okay? So the AP Physics C exam has always been that way. Now, this year is the first year, of course, though, that they're adding a 4th problem. They're adding a bunch of multiple choice, but they're upping the time. So how that works out, I can't predict perfectly, but just so you know, it is not an easy test to finish. So you want to be, managing your time well.
You were the lab rats always.
You guys are lab rats, yes, exactly. Now, if I got a t-value that was negative and positive, because I'm going to get 2 answers, what do I do?
Just take the positive one.
Only positive value, right? No negative times in physics. We know that already. Okay, let's go to the next one. Let's say I'm given the following. Let's do it this way, actually. All right. Given the following velocity time curve, determine when the acceleration is at a max. And I'm going to give you some values here. Determine when the acceleration is at a max.
When they say determine an acceleration is at a max, does that include both positive and negative values?
That's a great point. So technically, if they wanted to know when it was positive or negative, they would say the magnitude of the acceleration. If it just says when is the acceleration a maximum, you're looking for only a
Positive value.
correct, because acceleration is a vector quantity. But if I said when is the magnitude of the acceleration, which is probably going to be a follow-up, it may give you a different answer, right?
Right.
So if I wanted to know when acceleration is a max, what am I looking for in this graph? What am I physically looking for?
The steepest upward slope.
The steepest upward slope, because I want it to be positive. And I know the derivative of velocity is acceleration. See how I'm putting velocity now up? So I know already that I'm looking for the derivative. The derivative is the slope. I would think what? This is probably the steepest point of the graph, right?
Right.
So I would say from 0 to 2 seconds. That's when the acceleration is greatest. It happens to be a constant in that range. It's a linear function for velocity. So the acceleration is constant right here in this region. So I can't give a specific time. I have to give a time interval. Does that make sense?
Yes.
It's not a given instant. Now, if I said the following, determine when the acceleration is equal to 0, what would you tell me? 0 acceleration. Conrad.
Would it be around?
Say again? Well, I don't want you to just give up on it. If we look for max acceleration, you found the slope. I want zero acceleration. So when is the slope zero is the question I'm asking, right?
It's at, it's a straight line.
Yeah, very good. So from 2 to 5, right? From 2, give a time period, from 2 to 5 seconds. Is there any other instant where it's equal to 0? You said yes right away. At 7. Anytime you reach a max or a min, your acceleration is equal to 0. Because what's happening there?
You're changing direction.
No.
Or you
That would be a
Okay,
position
yes,
graph.
yes, yes.
That would be a
You
position
go
graph.
from slowing down to speeding up.
You go from, in this case, decreasing velocity to increasing velocity. Let's just use those phrases. Because technically, if you're on the negative side, it's not always the same, right? Remember the speeding up thing is different there? Okay. So when you go from a decreasing velocity to increasing velocity, you have to cross 0. And think about it. You did this in calculus already. I'm going to draw for you. Ready? Negative, less negative, less negative, less negative, suddenly 0. Then positive, 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 right? That's what's happening here. That's what my tangent line looks like each piece along the way. So I have to recognize off the bat here that I do have a second point of 0 acceleration, not just that time interval. Part C, the magnitude of the acceleration is a max. When is the magnitude of the acceleration a max? And for this one, I want really an instant. I know it is not very clear perfectly, but there is an instant where the magnitude of the acceleration peaks in this problem. Do you see it already? Where is it?
It's at 5.
It's at 5. And take a look. At 5, look at the slope of the tangent line. Do you see that slope?
0.
It's practically almost negative infinity, right? See how steep that is in the negative direction? And then it gets less negative and less negative. So it's most negative at 5 when it hits that cusp. You know this phrase yet? This is called a cusp? Okay. As opposed to a corner. This is a corner. When two linear functions come together, it's a corner. When a curve and a linear or two curves come together, it's a cusp. At a cusp, you have no what?
Derivative.
Good. No definition of the derivative at these locations. So technically, 5 is right, but what is the answer really? Just
As the limit as t approaches 5 from the right.
well done. Nicely done. It's the location at 5, but from the right. Just after 5 is what we're talking about. And that tangent line is the steepest. It's steeper than the red line. It's steep, though, in the negative direction, which is why I can use that answer, because it says the magnitude, which means absolute value of acceleration. When is the absolute value of the acceleration the most? And it is that yellow line there. Let's say this number here, we're like, I don't have values on the y-axis, so I can't get a value. I'm using a value that I'm picking. Say this is like 7, this would be like negative 10. And if I take the absolute value of negative 10, 10 is greater than 7. So the magnitude of the most acceleration occurs actually in the negative sloped region. What else? Okay. In what regions is the acceleration changing? In what regions is the acceleration changing? When is it changing? Or let me ask this, at what regions or at what instances? Either one is okay, I'll answer that. I'll take both. At what instances or in what regions is your acceleration changing? I know you got it, so give me a minute. Let me ask another way. If I ask is what regions is the acceleration changing? How do I relate acceleration again to velocity? How are they related to each other? Use the word derivative to relate them. How is velocity and acceleration related? Use the word derivative.
The derivative of acceleration is velocity.
Other way around?
So the derivative of velocity is.
All right, so the derivative of velocity is acceleration, and I want to know when acceleration is changing. When it's changing. So really I'm asking, when is the derivative of this function changing? So in the beginning, is the derivative of this function changing or is it constant? What's the derivative of a linear function equal to?
I was going to say 2.
2, sure, a constant. Any linear function, its derivative is a constant. So if I look in this region right here, if I take the derivative of the velocity function here, I'm going to get a numerical value. Let's pick a velocity function here. Maybe this is like 5t. And this function here is the velocity in this page. Let's say this is 10. This is equal to 10. And then this is a curve down here. Let's say this is equal to t minus 7 squared, okay? Because that's curved, so the bottom is there. And then here, this is like, let's say this is 1/2 t minus 7 squared. It's less concave, okay? So these are my pieces. It's a piecewise function along the way. That's how you need to visualize it. So when I take the derivative of 5t, what do I get? What's the derivative of 5t? Just 5, right? You should all be able to say that. Derivative of a linear is just a coefficient. So if the function is 5t here, then the derivative is just 5. Therefore, the acceleration is just 5 in that region. It's not changing at all. So no change in acceleration here. How about the next part? From 2 to 5. What do you think from 2 to 5, Vita?
It goes from 5 to 0.
Okay, good. So the acceleration goes from 5 to 0. So where would there be a change in acceleration? At 2, exactly. Very good. So we're not looking in the time period from 0 to 2 or the time period from 2 to 5. Because in those two regions, acceleration is constant and acceleration is constant. But here is where the acceleration changes at 2 seconds. Nice. Now, after 5 seconds, when does acceleration change? Does it change at 5, from 5 to 7, at 7, from 7 to 12, or at 12? You see all those options I just gave you? Tell me.
Isn't it changing at all?
Very good. How come?
Because at 5 it goes from 10 to the t minus 7 squared.
And the derivative of t minus 7 squared is what? What is not the? I don't want the exact answer. But what does it become? What type of function does a quadratic derivative become? Linear. And that means that if it's linear, there's still t in the derivative of that, right? So as you plug in different t values into your acceleration function, you're going to get different acceleration values for the rest of the entire problem because I have a quadratic. Nice job. Well done. The entire rest of it. And we could show that, obviously. You can bring this down and take the derivative. This becomes 2, t minus 7 to the 1. And then this is something you're going to learn about called the chain rule. When you have a function on the inside of your power, you multiply it by the derivative of the inside afterward. You'll learn about this soon. But the derivative of t minus 7 is just what?
7. Or negative 7. No, it's 1.
It's just 1. So it doesn't actually matter. But if you look at your derivative, it's 2 times the quantity t minus 7. So the acceleration function in that region is given here, which tells me right away the acceleration is definitely changing because it's a function of time. But in the first two regions, 0 to 2 and 2 to 5, the acceleration function is not a function of time. It is not a function of time there. Okay? How we doing?
I just need to write down.
It's a lot of info. I know it's not easy. It's not going to always click right away, and it's going to take a little time. You're going to see a lot of problems like this on the exam, though, where you're given either a graph or a function, and right off the bat, you have to work with either its derivative or integral. Let me see how I could ask another question about this one. Oh, here you go. Ready? When does the object change directions? When does the object change direction? Vita?
At 5 seconds until like 7.
5 to 7. I saw other hands. Agreed? 5 to 7?
Yeah.
Agreed? You're all wrong.
Wait.
You read it as a position function. Come on, it's not a position function. What is this?
This is a velocity function.
It's a velocity function.
And it never changes.
It never changes direction. For a velocity function to change direction, it has to cross the t-axis. Right? It's got to cross the t-axis for a velocity function to change. Be careful, please. That is a very common lead-up question. They do that all the time. Because you just want to give an answer, don't you? You want to have an answer. You want to not say, it never does. And you know what? This kind of question will be a follow-up in like a FRQ where you have a graph already given. Or you have to create a graph at some point. And then you're given these follow-up conceptual questions about that graph that you made or about the graph that was given to you. Okay? Don't fall into the trap. And I asked it so convincingly on purpose that way because I wanted to lead you into that. I was really just leading the witness there in a negative way.
It's too easy, this 5 to 7.
It is too easy. I know. It's when you said it right away. And Gustav and Kyra both went, yep, that's right. And I'm like, no, come on. All right. So changing direction. Never. All right. Now we get to the harder stuff. All right. So I need you to like really stretch your brain for a little bit. Josh looks like he's going to fall asleep. Josh, you want to get some water? You can. I don't mind. Okay. Yeah. It's okay. It's early.
Can you fill in my water bottle, please?
Yeah, look at this guy. What a nice guy. He's filling up his water bottle. What a great guy. Josh, I'll give you a minute to get your water and come back, and then we'll go over this. So the next thing is going to kind of stretch your brain a little bit, okay? So I want you to be ready for that. I just need a little water myself, and I have it right here. So you see how last year's course compiles to this one, and how like I can't spend time going over how to solve, basic function problems where an object is launched straight upward. How long does it last before it's the ground? Like that stuff you got to be able to do already. Like we can't spend time. There's so much calculus stuff that we're going to be doing in place of that other stuff, which is interesting because some of the schools teach this course without ever having taken physics. Like they'll teach AP Physics C with no physics course as a prerequisite, but most of those schools that do that meet every single day for class. And meet for like 60-minute periods. Although we have a pretty good schedule this year. We have 5 periods a cycle. It's pretty solid. I like that. Last year we only had 4. Oh, last year I didn't teach it, but there was only 4.
I like how this you have to calculus to take this course because they
Yes.
make so much. Like I like how we're learning the same things.
Yeah. Well,
Or we're learning how to apply that.
it's awesome when they're co-recs because they actually apply to each other. Again, back to other schools because I look at what other schools do for curriculum-wise. Some schools will teach this course without calc knowledge. And then the students that aren't in calc, right, because they're in pre-calc, have to learn it on their own.
So they don't
Yeah.
teach, they don't teach it.
So like it'll be juniors in pre-calc that'll be allowed to take this course. And those juniors are responsible for learning calculus on their own with this course so that they can keep up with it, which is like, that's not setting someone up for success at all. All right, so ready? Now we have to kind of really stretch your minds. Is your mind ready? All right, cool. Hold that water in there now, it's malleable. Well, that'd be your stomach, but still. So if I look at the first region of this graph from 0 to 2 seconds, we could see here what's happening to my velocity. Just tell me in your own words. From 0 to 2 seconds, my velocity is increasing. Very good. Increasing. What's happening to my velocity from 2 to 5 seconds? Constant, stagnant. Good. Could you tell me from 2 to 5 seconds how far this object has been displaced?
Yes.
No? Yes.
You just
Yes?
take the area
You take the?
you just take the integral.
The integral. Okay, but let's do it without calculus because we don't need calculus to do it.
You just draw a little box and then calculate the area.
That's still calculus.
I was just gonna say, we know the velocity and time is multiplied.
Thank you, Josh, for not overcomplicating things. So from last year, if you know velocity is constant, you had this equation. Remember this one? This was the only equation that did not involve acceleration. And the only region on this graph that doesn't have acceleration is where again? From where to where?
From 0 to 5.
No.
Oh, wait. From 2 to 5.
From 2 to 5. Good. So if I were to write delta x as its own, I would write it like this. Okay? By the way, this is just a shorter version of the long equation we use without the 1/2 at squared. All right? Just take a look at it, make sure it's clear. Okay, just drop this off. And doesn't this equation become the same thing? Look at the two. If I move x0 over, it becomes x minus x0, which is just delta x. And v0 is initial velocity. But if the velocity isn't changing, is v0 any different than v bar?
No.
By the way, v bar means constant velocity. Constant. So the point is this. I can multiply my velocity times my time. And now we're going to jump ahead to what Gustav was ruining for us a minute ago. Sorry, Gustav, I didn't mean to set you up for that. And I could look at this region, and I could just break it into a rectangle here. A giant rectangle in blue. And when I look at that blue rectangle, the width of that rectangle is 3. The height is 10. Does everybody agree with that?
Yeah.
The width is really the time. The height is the velocity. And then delta x simply becomes 30 meters. Does that make sense in that region?
Yes.
Because you would take 10 meters per second for 3 seconds, therefore 30 meters. Now, Why am I asking you about that region? Because when there's not velocity that's constant, when velocity is changing, we cannot do that. You can't just multiply a v value because velocity is changing, right? Again, when velocity is not changing, it's so simple. It's whatever the velocity is, which was 10 times 3. But every other region, the velocity is changing. So what I wanted you to see is what Gustav kind of was talking about here, is that it's really the area of this region that gives me delta x. Think about that for a second. The area of that region gives me delta x. So if I wanted to know how far the object travels from 0 to 2, I don't need to use a formula. I was just showing you with the formula a minute ago. I can use instead the area, which is what he was talking about. This is called the integral. We have to learn this now in this class. We're not going to do it crazy with it. You'll learn a lot more about it in calc. We're going to learn about applying it with area under the curve and how to do the integral as a power rule, as the opposite of a power rule. So if I wanted to know how far this object traveled in the first 5 seconds, I could sum together the triangular area with the rectangle I just got. Or I could just make a trapezoid. God bless you. It's a trapezoid. The bases are parallel, and this is the height, right? So 1/2 base 1 plus base 2, all times height. If you do a trapezoid, or the triangle here would be 2 times 10 divided by 2, which is going to be 10 total. 10 plus 30 means that from here to here, the object has traveled how far? 40 meters. The 10 from this, and then the 30, which was the area under this curve right here. It is very common for a problem to ask you something like this. When will the object reach 20 meters? When will the object reach 20 meters? Well, how many meters does it cover in the first 2 seconds, we said? What's the area under this curve? How many meters does it cover in the first 2 seconds? Be careful.
10.
Do the area. What's the actual area under this curve? It is 10.
It's 10. Yeah.
You said
It's 1/2 base 6.
correct. You said 1 to start.
It's
That's right. 10, yeah. So this area is 10 under here. So it does not reach 20 meters by the time it reaches 2 seconds. So we need to know when this is going to cover another 10. Well, it's a rectangle, right? And if the whole area is 30, I could just do what? How much of the rectangle? 1/3 of it, right? So technically, I'll notice here that this area is, and I'm going to get rid of this 5t for now, okay? This area is 10, and this is 3 sections of 10. Can you visualize that and split it in your mind? Because 3 seconds have elapsed in that time period, so why not break it into 3 regions, each region of 1 second length? So at 3 seconds right here, the object has moved 20 meters. At 4 seconds, the object has moved 30 meters. And finally, at 5 seconds, it has moved a total of 40 meters. So a problem is not just going to ask you how far has it moved. It might say, when has it moved this far? Or when has it returned to its original position? How is that possible? How could I get it back to its original position of 0? Can anyone come up with a way that they can think of a graph that would make that happen? Because I'll tell you right now, this one will never get back to its original position. Right? Just keep adding areas. What are you going to get? Is your number going to get smaller or bigger? If you keep adding all these areas, are they all positive areas? Right? If I did this area, I know it's hard to do right now. We're going to talk about how to do that with calculus. It's all little rectangles and stuff. But if I got all these areas and added them up, this number would just keep getting bigger. It was 10, then it was 20, then 30, then 40, and maybe by here it's at 60, and here it's at 80, and here it's at 100 meters. If I keep adding more areas, it's going to get greater and greater. So how is it possible for this object to return to where it started? Josh? We need a negative velocity to show moving backward and possibly heading back to where we started. So as Josh just said, we need a velocity function that dives beneath the t-axis. Well, in calculus, you're going to learn that those are considered to be negative areas or negative intervals. So if you have an area that's under the t-axis, you want to consider it negative. So watch what I'm going to do here. I'm going to just redraw this portion here. Okay? If I were to redraw this portion now, I can answer that question from earlier. When does the object stop? The object stops right here, just after 7 seconds, right? It stops right after 7 seconds, and it turns around, and it starts going in the negative direction. And you know what? If this total area here is 60, as soon as this area gets to 60, if I keep adding these little slivers, because I'm going to teach you in calc or how to do this, I'm going to keep adding these little rectangles. As soon as these little rectangles add up to negative 60, that means that this 60 it gained in motion here will be canceled with the 60 it lost in motion there. And it ends up where? Back where it started. We don't need a position graph to find like where does the position function get back to 0. That we don't need that to figure it out. All we got to do is look to see when the area on the positive side of the t-axis gets balanced with the area on the negative side of the t-axis. When that happens, it just means you move 60 or positive 60 meters in the beginning, then you move negative 60 meters at the end. Well, where are you? You're at 0. Positive and a negative yields 0. So area under our curve for the velocity curve will give us our change in position. We're about out of time. I want you to ask this question. What if I have an acceleration curve? What if I have an acceleration curve? If I do the area under that, what do you think I'll get? Think for a minute. Remember, you have position's derivative becomes velocity. Velocity's derivative becomes acceleration. We just said that if we do the integral of velocity, we get our displacement or our change in position. Conrad, what do you think? You get not just velocity, you're on the right track, but the what in velocity? The change in velocity. The integral of this curve gave us the change in position. The integral is called the net change, actually. It's called the net change theorem. You're going to learn about it in calc. If I have a function that's given and I integrate it, I'm given or I'm solving for what's called the net change of that function's integral. So if I have acceleration, it becomes the net change of velocity. If I have velocity, the integral becomes the net change of position. The same is true if you have like volumetric flow rate. You know how much the water is flowing. If you do the integral of volumetric flow rate, you get volume. It's the integral of a rate gives you the overall change of that quantity. You're going to learn about this a lot in your calculus course. That's what I wanted to get through today. I want to do another example or two, obviously still covering like other integrals, other derivatives, and I'm going to practice these with you. But what I'd like you to do for homework, let me just see where we're at. I had an assignment, but I got changed because I was late. I'll post the homework assignment, okay? I do want you to do something for homework though. Do we have a double tomorrow, am I right?
Yes.
So
Yes.
you can expect a quiz on linearization tomorrow. We haven't had one yet. We've done a lot of homework, we've done a lot of examples. I'm telling you now to expect a quiz on linearization. Okay, that'll be during one of the periods. It'll probably be like a 20 to 30 minute quiz. I'll probably give you some multiple choice and an FRQ. Maybe it'll be even one of the 2 periods. Okay? It'll be like, yeah, I know, because our tests are really like double period tests in this class. Okay, they're full length, so the quiz might be a full period tomorrow. I can tell you now, though, multiple choice and free response, both are possible for linearization tomorrow. Okay? All right, and we'll come back to this, obviously, in the second period tomorrow. Can you guys do me a favor? You got to really push Miriam to watch this video tonight.